I've got another chink in the puzzle. I knew these diodes had something to do with what's going on here. I am using this capacitor as if it were a piezoelectric crystal, quartz crystal. I'm causing it to vibrate. Why is that? Because I'm squeezing it with voltage by building up voltage on one side coming from these diodes. And that causes the frequency, it causes this capacitor to start to vibrate. Now normally it wouldn't do that because we're simply building up charge and we're not allowing it to discharge. Yet we're squeezing it by increasing a voltage beyond, probably, I'm speculating, probably beyond what it would normally carry. Normally I would suspect that something of such a low value, because normally I'd go higher, but apparently I had to go lower to get this thing to work. You know, I'm normally at 10 nanofarads for all of my capacitors, but I had to reduce this to a picofarad. So normally a picofarad capacitor probably doesn't store 450 volts. I believe, if I'm not mistaken, I have a lot of voltage building up there. Let's see if I can find the... Now I'm curious. I want to go find the picture. Where did I put it? 100 milliseconds. No, that's the inductive load. Well, let's see. Nope, not that one. No, not those. Oh, the inductive load, yes. Okay. The resistive load, inductive load. So, since this is a reading of the load 3, well, it used to be called load 3, now I've renamed it load 2, because this is not a load, this is a buffer. It has to stay there. So now load 3 becomes load 2. So the inductive load here is adjacent to the capacitor, and so its voltage, along with the voltage of the transformer, you know, they run in parallel, so we can use this as a guide here. So the voltage escalates at around, I don't know, it looks like maybe 50 milliseconds or whatever that is. It quickly rises, and then it plateaus somewhere in the vicinity of around 400 volts. And then the amperage, of course, rises very gradually. So, whoops. So, it could be we're compressing this beyond its normal capacity to hold a charge, you know, because we're not allowing it to release. You see, a normal tank circuit, the capacitor is free to discharge and charge. Isn't that the case? You know, let's go get a little tank circuit here. Let's go get ourselves a little tank circuit. Whoopsie. Do I have to worry about this? Yes, I do. Whoops. I'll edit this out. What can I say? Okay. Where am I? Tank circuit. No, let's do... Oh, that didn't work. What's going on here? God, now nothing works. Oh, this is bizarre. In the old days, I used to be able to. There we go. Alright. So no, that's not a tank circuit. Basics, Ohm's law, resistors, AC circuits, other passive circuits. Oh, wait, did I see LC? DC, light switch. No, LRC, critically damped. So it must have come before this. RC, RL, resistor capacitor, resistor inductor. I don't want any of those. Caps, series resonance, parallel resonance. No, that's not what I want. Is that what I want? No, I don't want that. No, there was a good example. Oh, I remember. I remember it well. Alright, critically damped. It's the critically damped one. So, we got this circuit, and when we apply this, we charge it up, and then we release the charge, and it oscillates ever so slowly and dies out. That's not fair. Ew. Let's try that again. Let's try that again. Critically damped. Charge it up. So now my inductor has more resistance to it. Oh no, critically damped is not what I want. Oh, I see. This is the problem. Oh, let's charge it up again. How come it doesn't oscillate? That's not fair. You know what the problem is? The frequency, the time step is too slow. See what I mean? I knew it. Yeah, the frequency is too slow. I want to show you a take circuit, but how can I do it if I don't have the right time step? Yeah, that's more like it. Right, see how it's dying out here. That's a normal. Alright. There we go. So a normal oscillator, you give it a charge, you give a capacitor a charge. There, see, that works. That works for me. It works. If it's good for you like it is for me. Alright, let's recenter this. Okay. Alright, so we give a capacitor a charge, and a capacitor coupled with an inductor. We charge it up, we release it, so that it's free to oscillate at its own resonant frequency. And of course it dies out, right? Because we got this resistor in the way. Let's charge it up again. So now let's charge it up some more. So what do we got here? We got the resistor. We don't want to look at that. We're looking at the capacitor and the inductor. And we don't really need to look at the capacitor, but let's look at it anyway. So now they're free to oscillate. And we'd expect that's what would happen under normal circumstances. This is what we would expect. And eventually it'll slowly die out depending on the resistance in the circuit. Okay? So this is what's normal. Normal behavior. But then we go over to this. This is not normal behavior. The voltage rises. So I think what's going on here is that the use of diodes shoving voltage over to a capacitor you know, in a DC fashion. You know, the input is AC and the output is DC before it leads to the capacitor. Of course, is very unconventional, but we're squeezing the dielectric of a capacitor. And then it starts functioning like a piezoelectric quartz crystal. And so now it starts to vibrate. And guess what? When we look at, what is it? Oh, I love to look at examples. Oh, I know what I'll do. That's right. I won't have to. Okay, let's see. Is it Bohr's law? Bohr's model? I forget. Niels Bohr. Atomic physics? No, that was not it. Niels Bohr. No, that's not it. Wrong one. Sorry. Okay, temperature, pressure, relationship. Here we go. Gas laws. Finally. There's no charts. I love charts. That doesn't look like a chart. References. Well, let's see. What does it say? The gas law was developed at the end of... I gotta read this. It's too tiny. At the end of the 18th century, when scientists began to realize that relationships between pressure, volume, and temperature of a sample of gas could be obtained, which would hold to approximation for all gases. Gases behave in a similar way over a wide variety of conditions because they all have molecules which are widely spaced, and the equation of state for an ideal gas is derived from kinetic theory. The earlier gas laws are now considered as special cases of the ideal gas equation, with one or more variables held constant. Oh, so this is thermodynamics of an isotherms of an ideal gas. Pressure, the most frequently introduced form is... Yeah, that looks like, this looks like it. So it's the ideal gas law, is what it is. Oh, here's this again. Avogadro. Oh. Boyles, Charles, Gay-Lussac, Avogadro combined ideal gas law with the Boltzmann constant. Oh, now we're getting somewhere. Boltzmann constant. Now what's that all about? Physical constant named after its discoverer, Ludwig Boltzmann, which relates the average relative kinetic energy of particles in a gas with the temperature of the gas, and occurs in Planck's law of black body radiation and in Boltzmann's entropy formula. Ooh, we'll just stick with this. Boltzmann constant. So anyway, it has to do with this stuff. So here we are, and what was the point? We're pressurizing this capacitor with voltage. See, we don't have to do Tesla's special, what was it, that patent on pressurizing a capacitor, because we're not trying to change its equivalent series resistance. This thing over here. We're not trying to, of the dielectric, we're not trying to do that. Yet we are. Well, at least, oh my God, not by applying mechanical pressure, but by applying voltage pressure, if we can call voltage pressure. I don't know. Most people do, but sometimes I get other opinions. For the moment, let's just call it that. So we're applying voltage, which, as far as piezoelectric crystals go, is equivalent to pressure. And that's probably why people talk about voltage and pressure in electrodynamic theory as equivalent or parallel terms anyway, because piezoelectric crystals work that way. So we pressurize the capacitor with voltage, and it starts ringing beyond what it normally would oscillate at, because the voltage is going up higher than what it would normally carry. And because of this relationship, we raise the temperature, we raise the pressure, the frequency. Ah, the frequency. That's the kinetic energy of the particles of a gas, right? That's the frequency, the kinetic energy. So we've raised the kinetic energy of this little capacitor simply by pressurizing it, and that raises its frequency. Got it. That's why this system escalates. I knew it had to do with this capacitor and the diodes. I just couldn't figure out why. Because we're pressurizing it beyond its normal ability to carry a charge and disallowing it to discharge. You would think it's going to try, you know? The voltage keeps coming in and it's going, no, no, I want to release, I want to release. And it keeps coming in, no, no, you got to take more, you got to take more. Sorry, my falsetto broke there. And so it keeps trying to release. Right there, we've got oscillations right there. And the more it gets pressurized, the more quickly it tries to get rid of those buildup of voltage, because it's being pressured to do so at an ever increasing rate up to a certain point, you know, and it can't increase its pressure anymore because it can't hold it anymore. Well, I don't let it. Ah, see? That's why, because I don't let it. You see, this is why this goes up and then all of a sudden stops. You know why? Because this is the very first surge, or the very first spark gap release. Where can we find a graph? Nope, wrong direction. Here, no, here. So we have this at, it looks like, well, if we divide 53, let's see, 53 minus 42 is 11. So I'd say that's around 45 milliseconds, which looks like, for the first release, it looks like that's about correct, because this line here is 200 milliseconds. So that would be 100 right here, and that would be 50. That sounds about right. Somewhere in the 40 range here, 40 milliseconds. So at 40 milliseconds, this stops surging and then begins to plateau only because of the spark gap is now firing. Because this capacitor did its job and is free to oscillate, unlike this one over here, and dumps its charge and says, hey, look, it's time to... We've got enough voltage difference between the two sides of this capacitor in parallel to the two sides of the spark gap. It's time you fire already. And when it fires, it realigns the current with the voltage so that the surge can stop surging. Now, I still don't understand why the voltage and the amperage separate by half a cycle, but at least now I can see why the frequency goes up. Because I don't have, let's see if I can find for you the graphic image that shows the escalations. This is so fascinating. I had a slow build up. Whoopsie. Let's see, I've got so many images here. You know, I don't think it's here. I have to go to another place to find it. I'll just go through here. Maybe we'll... Whoa, what was that? Ah, here we go. 10 microsecond duration of a surge developing from a 2 megahertz input frequency. So I created circumstances to try to elevate the conditions so we can see that the frequency is definitely increasing. We start out with... See, this was a complaint over at Stack Exchange. Well, all we see are, you know, what I showed you earlier, which I won't go fetch because it took so long to get here. Triangular waves. No, they're not triangular waves. The simulator can't catch up, can't keep up with the increasing frequency, and so all I can do is approximate a sine wave by the use of drawing it as a triangular wave. But you can see right here, this looks like pretty close to the curvature of a sine wave, and then it increasingly becomes more like a very jaggedy, whatchamacallit, triangular wave. Whoopsie. Little butt crap. Butt crap. Right, butt crack images I was going to use. Let's see. Where's the one with the... It's not here, is it? I'm looking in the wrong place. Oh, hi, Eisenhower. No, it's not here. I'm looking in the wrong place. Oh, there's Joseph Newman. Yeah, I'm looking in the wrong place. Okay, I gotta look in a different place. I want to show it to you, but I can't show it to you if I'm not looking in the right place. Where are we? Here we are. Alright. It's in here, I'm sure it is. At least I thought it was. It's not in here. Oh my god. Oh, where did I put it? Huh. I have no idea. Oh, brother. Oh, I know. I think I put it over way over here. Here we go. Stack exchange, of course. What was I thinking? Finally. Okay, so here we've got the voltage separated from the amperage. Oh, there's a good example of noise. The blue is the current, and the red is the, what is the red? Oh, the RMS of the current. So the blue is the raw current, and the red is the RMS of the current. And that's what comes out of the sine wave generator. In this case, it's a third of a nanoamp, which is feeding this circuit, this particular example that is somewhere. It's up here. It's this thing up here. Is it this one? Yeah, maybe. Let's see. Let's expand this and find out for sure. Oh no, this was the special case where I rectify it to create a little DC condition over here. So we had 50,000 hertz, and that's where that came from. So see, I have 10 nano here in this capacitor, and 1 nanofarad over here adjacent to the spark gap. So it varies, you know, depending on what you do, what you try to do. Anywho, here we go. This is it. But I put them all together, but they are separate. So here's 50 microseconds duration. Oh, it's going backwards. So we're going backwards here. Sorry for the noise. Somebody's working on the roof. So let's go to the beginning. Here. So at 2 megahertz input frequency during a 750-second surge. Oh, that was supposed to say nanosecond. I'm sorry. Yeah. 750 nanosecond surge. So it's slightly less than a microsecond. So we see this nice sine wave, and then we see a frequency riding on top of it. Now this sine wave, I think, is the input frequency, if I'm not mistaken. 2 megahertz. See, that would be, let's see, right around here at 500, half a nanosecond would be 2 megahertz, right? Isn't a nano a mega? You know, a milli is 1,000, a micro is 1,000,000, and mega. Well, a mega is the opposite direction, so you went kilo to mega. No, I'm wrong. It should be microseconds. Oh, no, right. It's half a microsecond. Right. So at this point here, at 500 nanoseconds, it's half a microsecond, which is equivalent to 2 megahertz. So this is the 2 megahertz sine wave input, okay? But then we got this other frequency coming. Where's this coming from, right? And it's escalating. It's riding as a carrier, piggyback, on top of this 2 megahertz frequency. It's smaller amplitude. You know, this is a much bigger amplitude. This is, what is this? This is, looks like 600 picovolts. Right, these are volts. Now, I call it rotor here, but this is the transfer coil. So we get these little sine waves, but they're triangular because the poor simulator can't catch up, you know? And Whoops. And so this is a 3/4 of a microsecond window. And then now we come to about the same. No. Oh, this is less. Oh, it shows it forming better. Yeah. Anyway. So now we go to 800 nanoseconds instead of 700 or 750. And we see it ironed out. On this curve, it's ironed out a bit because we see it rising here. See, so this is going to be the rise, the surge. So with the rise of frequency comes the rise of voltage. Uh-oh. Well, not quite. So here's the beginning sine wave. But it's rising in the sense that it's, oh, I see. It's going to be a higher sine wave. So we're adding voltage to the base voltage, you know, so we've got the sine wave, that's the base wave, but we're adding voltage to it because we're adding this carrier frequency on top of it. So it's benefiting from the carrier frequency riding piggyback, increasing its frequency, is adding its added voltage or energy, potential energy, to, in the form of increased frequency, to the voltage energy value of the carrier wave. And as it does so, it keeps getting more and more rapid, and now it turns into Gabriel's trumpet. If you look that up on Wikipedia, it's a great article on Gabriel's trumpet. The surface area of Gabriel's trumpet relative to the volume. It's a fascinating subject, and it has to do with infinite mirrors and whatnot. So as we pan out over a longer duration, this is 20 microseconds, it turns into Gabriel's trumpet. And now we've got our hyperbolic surge. So, see, that's the progression as it goes from top to bottom. It's a fascinating topic how this thing develops. You know, it's really fascinating how it develops, starting with 700 nanosecond window to 750, and then it goes to 800. And then we get to 10 microsecond, and then we go to 20 microseconds, and then 50. And so you see it keeps getting tighter and tighter because it's escalating. The curve keeps getting steeper and steeper. So it's growing at an exponential rate. That's pretty obvious. And now this says, oops, it's stopped. Because that's why I don't do 2 megahertz, because I can't carry it long enough. I usually carry it to 1.35 megahertz because that's my limit. And so it breaks down at 58 microseconds, and I get this internal time step too small and transient analysis error message, and the whole thing is bottomed out. So this is really a fascinating topic as far as I'm concerned. This is the rotor. Yeah, this is the rotor. Oh, isn't that pretty colors? I love it when I do it this way. Now this, I'm coming in close for a closer view. 100 nanosecond time step. No. Oh, 40 milliseconds. Well, what is this 100 nanosecond time step? What's that all about? It's 40 milliseconds. I don't know. Oh, I was changing the time step in the simulator to see if I could bypass the error message, and of course it failed. It never worked. You know, they were complaining to me on Stack Exchange, and I was trying to accommodate them, and it never worked. So here's the C1. Now C1 is alongside the... No, it can't be alongside the spark gap. How can that be? Oh no, yeah, right, C1. Every time in each schematic, I number it differently. So C1 is the one in question that's increasing the frequency. And so we go back to here. Here. So this is C1, and it plateaus. And this is where it starts, the wedge-shaped staccatos start to form. Well, they drop off because the spark gap is doing its job and releasing the circuit from a constant exponential surge so that it doesn't, blow up. so that it doesn't turn into, it's doing this instead of doing this, instead of doing this. So let's go back to the other one. Get away from this. Here we go. So at least I still don't know why the voltage separates from the amperage, but at least now I know how the surge develops. Despite the fact that you would think the separation between voltage and amperage is a causative factor, but maybe not. Maybe it's merely an effect rather than a cause. It's one of various side effects, such as the surge itself is a side effect. Sorry for the noise again. It's roof day. Scrape. I'm in the dentist's office. See, he's working on my teeth while I speak to you. The teeth cleaning gal is cleaning my teeth. Scrape. They probably do need teeth cleaning. So they're cleaning the roof. Okay, so I'm not going to repeat myself, but maybe for emphasis. So let's recap. The diodes are taking an AC input from the sine wave generator and feeding a DC to the capacitor here. And it builds up voltage, and it starts to beyond what it normally can hold. And it starts to vibrate because it's trying to release it against the diode's better judgment. Its judgment and they are fighting with each other because they're saying, no, you don't get to release. And the capacitor says, hey, I'm ready to release. And so it starts to oscillate regardless of the fact of whether or not it's allowed to. And so it starts to oscillate, and because its voltage keeps going up, it oscillates faster and faster because we're squeezing it. So naturally, it's going to oscillate faster as we continue to squeeze it. And it would continue to oscillate faster and faster, if not without limit, if not for the spark gap eventually firing and releasing this poor capacitor from an increase of voltage. So instead of continually increasing, it plateaus, more or less, as we've seen already. And I'm sorry. I have to keep saying I'm sorry because that's all I can do. I had to say this. When I have the thought, if I don't say it right away, it's gone. It's history. I got short-term memory. For all my intuitive ability of appearing to be all-knowing, I retain absolutely nothing. Let me tell you, I will forget everything I tell you. That's why I make these videos as notes to whomever. I never watch them again, usually. Almost never. A little respite. Oh, here he goes again. Yeah, he's doing his job. Work harder. Make more noise. Okay, so that's why we have an increase of frequency. And of course, when you have frequency, you have potential energy. I've seen it somewhere on Wikipedia that frequency and potential energy are one and the same. So we're building up potential energy here, which, when it spills out back into the circuit, converts into kinetic energy, which is great, especially down over here. They can use it, these coils. But why anything else is going on, I don't know. But at least we're getting somewhere. Step by step, we're solving how this circuit works, and the whole intention was to convert it into monetary policy. But I think I've already covered that in a prior one, micro crypto network currency network. And the noise is really annoying, so I'm not going to try to speak over it any further. So you got that idea, and I hope you enjoyed this video despite the noise. Sorry about that. Next video won't have that noise.